Alright, so in this quiz we are just going to be revising CC7. It's a topic that we did in year 10 about structure and bonding. We were really good at it in year 10, but I'm conscious that we haven't spent much time in it in year 11. So the purpose of this quiz is to get back to where we were in year 10 and make sure we know this stuff really well. It comes up on both papers, it's worth a lot of marks. So the first one is just sodium fluoride is an ionic compound. Describe how sodium and fluorine atoms interact to form a sodium ion and a fluoride ion. Alright. If sodium has a positive charge, it's got a positive charge because it lost an electron. And if a fluoride ion has a negative charge, it has a negative charge because it gains one electron. But you're asked to describe how they interact. So in order to get the marks here, what you're going to have to say is that sodium loses one electron and fluorine gains the electron from sodium. Okay, if you just say fluorine gains, but you don't say where it gets the electron from, then you're not describing how these two interact. So you can say sodium transfers one electron to fluorine, fluorine gets one electron from sodium, anything along those lines, but make sure you're telling me that sodium loses, fluorine gains, and sodium gives fluorine that electron. Then why does sodium chloride conduct electricity when molten but not solid? You have to talk about molten and solid. You can't just choose one. So I'm going to say when molten, the ions are free to move. When solid, ions are not free to move. Okay, so I'm talking about molten and solid. You have to say ions, and in the mark scheme it is accepting charged particles, but it doesn't always. It's not delocalized electrons, that's just wrong. So ions are charged particles, but I would say ions, it's more specific, and some mark schemes require that. So molten, the ions are free to move, and when they're free to move they can carry current. When it's solid, those ions are not free to move. If they can't move freely, they can't carry current. The next one here, a 6 marker, asking you to use the properties to decide the structure and bonding. Now when you're asked about structure and bonding, all they want to know is it ionic, is it covalent, is it metallic? That's what they're asking. You need to use the properties to work out which one it is. And I think the easiest one to work out is always, if you look at ability to conduct electricity, the first one here, A, doesn't conduct when solid, does conduct when molten. And as we just saw over here, when we had an ionic compound, that is a typical property of an ionic compound. Ionic compounds conduct when molten, they don't conduct when solid. And it's got a high melting point. So all of this is consistent with being ionic. The next one conducts when it's solid and when it's molten, okay? And it's got a really high melting point. Now the thing that conducts when solid and molten is a metal. Alright, metal have delocalized electrons, they conduct when they're solid, they can still conduct when they're liquid, and they've got high melting points. Metals are solids at room temperature. The last one here doesn't conduct electricity at all, and if you look at the melting point, it's much lower than the other two. This is telling you that you have got a simple molecule, so a simple covalent molecule. Now once you figure that out, you do need to be able to explain it. You need to be able to explain their properties in terms of their structure and bonding. So I'm not going to write out the whole answer, but I'll just give you an indication of what you would say. I would start off by making it nice and clear. A is ionic. If it's ionic, its structure is giant ionic lattice. But you need to explain how you knew it was ionic based on these properties. So you'll say ionic compounds have high melting points because, and this is where you'll need to say ionic compounds have high melting points because there is a strong electrostatic attraction between oppositely charged ions. You'll then explain why it conducts when it's molten but not when it's solid. It's the same answer we wrote over here. You'll say ionic compounds conduct electricity when molten because the ions are free to move. They do not conduct when solid because the ions are not free to move. Alright, so you're going to explain both of those properties. Then you're going to move on to B. You're going to clearly say that B is a metal. If it's a metal, its structure is giant metallic lattice. And then you're going to explain the properties. So we see that B has a high melting point. Again, if it's got a high melting point, there must be strong attractions. Again, your strong attraction here is a strong electrostatic force of attraction. So just like ionic, you've got a strong electrostatic force of attraction, but this time that attraction is between positive ions and delocalized electrons. With the ionic, it was between oppositely charged ions. With the metallic, it's between positive ions and delocalized electrons. You can say it always conducts electricity because it has delocalized electrons. And then C, you're saying it's a simple molecule. Its structure then is just simple molecular. You'll say it's got a low melting point because it's got weak intermolecular forces. And you'll say it cannot conduct electricity because it doesn't have free moving charged particles. Now, do you need all that to get 6 marks? No. If we take a look here at the mark scheme, you'll see that to get 6 marks, you need to identify the correct structure. So you need to know ionic, metallic, simple, covalent, but you only need to explain the properties for 2. So just say you knew nothing about metals, you copped on that it was a metal, but you couldn't explain why, you can still get 6 marks. So here it tells you all of the things that you could say, but you don't need all of this to get 6 marks. So you can describe the ionic compound in detail if that's the one you know. Then you can just say B is a metal and move on. And then you can move on to C and say how you know it's a simple molecule due to those weak intermolecular forces and it has no free moving charged particles. So describing 2 in detail and just mentioning the structure of the third is enough. Okay. If you want to do a little bit of each one, that's also going to be enough to get you to the 6 marks. Okay, so just write about what you know. It doesn't have to be even between all 3. Right, the next question, this is the one that came up on your mock. You're told you've got sodium chloride and you've got water and you're given the boiling points of both. They first want you to explain this difference in boiling points. Why does sodium chloride have a much higher boiling point than water? They want you to do so in terms of structure and bonding. So this is, again, you're talking about, is it ionic, is it metallic, is it a simple molecule, and what difference does that make to the boiling point? And once you've done that, you're going to say how you can separate sodium chloride from water. All right, so we're going to start off with sodium chloride. All right, it has got a high boiling point, but a high boiling point isn't enough to tell you if it's ionic or if it's metallic. You need to look at the elements involved. Okay, you've got sodium, which is a metal. You've got chlorine, which is a non-metal. And if you've got a metal and a non-metal, it's going to be ionic. If it's ionic, the structure is giant ionic lattice. And you need to explain why the boiling point is so high. So you'll say here, you've got a high boiling point because you've got the strong electrostatic attraction between oppositely charged ions, needs lots of energy to overcome. All right. Then you're going to talk about water. Water has a much lower boiling point, so you need to be able to explain why. If we look at water, water is obviously H2O. Okay. Hydrogen's a non-metal, oxygen is a non-metal. Water is just a simple molecule. Okay. So water is a simple molecule. If it's a simple molecule, that word molecule will hopefully trigger the word intermolecular. If it's a simple molecule, it's only got weak intermolecular forces between molecules. Not a lot of energy is required to break, and therefore water has a lower boiling point. So you're explaining why sodium chloride has a high boiling point, why water has a low boiling point. This one's got strong electrostatic forces, this one's got weak intermolecular forces. Once you've done that, you need to suggest how you're going to separate them. Now, in your mock, a few of you wrote about evaporation, okay? So when we just stick the sodium chloride, so this is just salt water, that's what this is. You put that into an evaporating dish and you heat and you evaporate off all of the water, okay? But if you look at the question, at the end you want to have the water. If I just heat it with a Bunsen burner, all of the water will be evaporated. I'll be left with the salt, but the water is gone. So instead of using evaporation, when we want to keep instead of using crystallization, when we want to keep the water, we have to use distillation instead. So you can just briefly describe how you would distill something. So you heat, the water evaporates, then it cools in the condenser, it condenses, and then you can collect the water again. Okay, so it's a similar process to what I've described above, but you've got a condenser attached which will cool the water vapor, turn it back into a liquid and allow you to collect it. Right, the next one over here, 37. They give you two substances. You said you've got solid ammonium chloride and you've got ammonium chloride solution. In one, it says the solid, the lamp does not light up, and in the solution, the lamp lit brightly. Explain the results, all right? If the lamp lights, that means that this is conducting electricity. And if this one doesn't light up, it means that the solid ammonium chloride is not conducting electricity. So what type of substances do we know conduct electricity when they're in solution, in liquid form, and don't conduct when they're in solid form? Again, it's ionic, all right? So you're going to say in the solid ammonium chloride, I'm just not going to write that out, in solid ammonium chloride, you're going to say the ions do not move freely. So do not conduct electricity, or do not carry current. And then you're going to say in ammonium chloride solution, the ions do move freely, they can carry current, and they can conduct electricity. So this one's for 3 marks. Let me find it on the mark scheme. Yeah, okay, so that's all you need, effectively, that's all you need to say is the solution conducts electricity, the solid does not, and then you explain why. The ammonium chloride contains ions, yes, both cases it contains ions, but in the solutions the ions can move, and in the solid the ions cannot move freely, okay? Just in case you get confused, you might not, but ammonium chloride is actually NH4Cl. That's the formula for ammonium chloride. There's no metal in ammonium chloride, so you might wonder, why is it ionic bonding if it doesn't contain a metal? If we think of our actual definition for an ionic bond, it's just the electrostatic attraction between oppositely charged ions. Ammonium as an ion is positive, chloride as an ion is negative. You do have oppositely charged ions in ammonium chloride, therefore it's ionic even without a metal. It's the only example you'll ever come across where you've got something ionic that doesn't contain a metal, because ammonium is the only positive ion that doesn't have a metal. Just as an FYI, it is ionic bonding. The next one, why does barium have a high melting point? All right, barium, if you look at its position in the periodic table, group 2, it is a metal. Why do metals have a high melting point? Look at the answer from the mark scheme, okay? But you need to talk to me. Anything with a high melting point, it must have a strong force, okay? And again, it's going to be a strong electrostatic force of attraction. This time in a metallic bonding, it's between a positive ion and delocalized electrons. That's what the force is between. And again, if you've got a strong force, your last mark is going to go for saying lots of energy is required to break that force. This one we've seen many times, okay? Why does graphene conduct electricity? Typically, covalent substances don't, but this one will, because it's got delocalized electrons. Just saying that, though, is not enough. It's for 3 marks. You have to tell me why it's got delocalized electrons. Carbon has got 4 electrons in its outer shell. In graphene, each carbon only forms 3 bonds. That means each carbon has 1 electron left over that can move freely. So on the mark scheme it says carbon has 4 electrons in its outer shell, 3 electrons are used to form bonds, 1 electron is left over, and these electrons are delocalized. Now be careful, don't just say graphene has 1 delocalized electrons. Each carbon supplies 1 delocalized electron, but there are billions of carbons, therefore there are billions of delocalized electrons. Why does potassium chloride have a high melting point? Again, we need to identify what type of bonding do we have here. I've got potassium, which is a metal. I've got chlorine, which is a non-metal. Therefore, this is ionic bonding. If it's ionic bonding, you're going to talk about the strong electrostatic attraction between oppositely charged ions. Therefore, lots of energy is needed to break. In all of these questions you get a mark for saying energy, so even if you can't give me anything else, if it says high melting point, say lots of energy is required. If it says low melting point, not a lot is required. The last one here, is this the last one? It is the last one. Ammonia and silicon dioxide are both compounds made of non-metallic elements, but you'll see there's a massive difference between the boiling point. So ammonia is minus 33, silicon dioxide 2230. I want you to explain why they're different. Now, if it's all non-metals, it can't be ionic, it has to be covalent. But there are two different types of covalent. There is simple molecular, which is what we've seen in this video so far, but then there is also giant covalent. Now, our typical examples of giant covalent are things like diamond and graphene. But there is another one that we don't actually study called silicon dioxide. And you might say, if you don't study it, then why is it coming up in this question? Well, they are telling you that it's non-metallic, which means you should be able to work out that it must be covalent. And if you see the boiling point being that high, you should also be able to infer that therefore it must be giant covalent instead of simple molecular. Okay, so to get your marks here, you'll just tell me that ammonia is a simple molecule, and you'll tell me that silicon dioxide, SiO2, is giant covalent. But then you need to explain how that affects their boiling points. All right. So if it's a simple molecule, like a molecule, think of intermolecular. If it's a simple molecule, it's only got weak intermolecular forces. So ammonia is a simple molecule with weak intermolecular forces. SiO2 is giant covalent with strong covalent bonds. Strong covalent bonds. And you'll end, as always, talking about energy. You'll say it takes more energy to break the strong covalent bonds than it does to break the weak intermolecular forces. That's why there's such a difference in the boiling point. There is a bit of just initial content to learn with this topic, and once you've learned the basic facts, you then need to practice doing the exam questions to make sure that you can apply the information in different settings. But effectively, once you've learned those key phrases, this should be a topic that you can do really well on. And as I said, it does come up in both papers.